Okay, here we're going to be looking at testing a claim about a mean, and we're going to again be using our one sample t-test. We're going to be looking at a different scenario here. So we have a claim that the mean pulse rate in beats per minute of an adult female is less than 76. And we're going to be looking at this, we're going to test it with a significance level of 0.01, and what we're going to use for our data is we're going to be using the data set. When you go through and you look at your statscrunch and opening statscrunch, again, remember they have the option to open up data sets. We're going to use, and you're going to use data set number 1 for the females. So you may want to pause for a moment and go ahead and open up that data set so you're ready to work with that. Once you've got that open and we're ready to go, we're going to take a look at our criteria here. So we're going to go through our same steps here as we did before. So our criteria here, again, we have a continuous random variable, or we have a population that's normally distributed, or n greater or equal to 30. So when we're looking at this, now we're looking at pulse rates here as something that's being measured. So it's going to count as a continuous random variable. Now our next thing we're going to be looking at, since we're not going to have a dichotomous, we're actually using it as a measurement. So the next thing we're going to do is we're going to look at our population. You need to look at that and tell me, what is our n? Do we have an n greater or equal to 30? Oh, we do. So we're going to be able to, our criteria are checked. So we're going to move on to our next step, which is identifying our test statistic. So we're going to go back to that table 8-2. And again, I strongly suggest that you just photocopy that and put it in your notes for how to solve these problems so you can reference it quickly and easily. So it's on page 381. Now we look at that, we see that we're going to be measuring a mean. So it's going to bring us down here to our mean that we have. So we have our mu that can be either the t distribution or the z distribution. We're not given what the standard deviation is for the population, so we're going to assume that it's not known, which means, again, we're going to be using our t distribution for solving this problem. So now we know we've got a t distribution, and while we're here, we're going to check real quick to make sure we've got our required information for using the t distribution. So again, we need to know what our significance level is going to be, our degrees of freedom, and we need to know the direction of the tail, whether it's a one-tail or a two-tail. So if we go through and look at these, we can identify each of these pieces in the problem. And we can see we got our sigma, our alpha is equal to 0.01. That comes straight from the scenario. And our degrees of freedom, we have an n of 40 for this particular data set. So we're going to subtract 1. And that means we're going to find that we get a degrees of freedom of 39. Now to determine the direction, whether it's a one-tailed or a two-tail, we're going to need to go look at our hypothesis for this information. So we're going to pop down for just a moment and finish doing our hypotheses and then come back. So if we come back and look at our hypotheses, first of all, what property are we solving for? Well, again, we're solving for the mean, so that's what we're going to be solving for. And the next thing we need to do is set up our null and our alternative. Now, I often find it easier to identify the alternative claim first because this tends to be what's specified clearly in the language of the problem. So when we're looking at this, we've got our mean that we're looking at as a property, and notice that when we're looking at the claim that we're being asked, that we're aiming for is having a mu lower than 76. So that is going to be our alternative hypothesis here. Mu is less than 76. Okay, and that's coming from the language over there on the left. And again, and then we're going to set our alternative. What would be the true if that alternative was not true? Well, again, we said is mu is going to be equal to 76. Okay, so our null is, our mean is in fact 76. Our alternative is the mean is less than 76. So those are our hypotheses. And we come back and we look at these and we connect these, and we can see then that we are going to be doing a one-tail test. And furthermore, we can tell about the directionality of it. Is it a left or a right tail test? Well, it is in fact going to be a left tail test. Okay, so well, we also know that we have a left tail test. So now we have these pieces put together. We can go on and we're going to be able to solve our problem, again, using the confidence interval procedure. So here we're looking at our confidence interval procedure. We're going to determine the left and the right interval boundaries, and we're going to do this via statscrunch. So we go through statscrunch. Again, similar to what we did before, you're going to be opening up your t-stats, one sample, and in our case, we're using the data, okay, because you're going to be using the data set that we have, okay? And once you have that, you should get an output that looks something like this. Now, your variable of interest is what you're going to click on over there, so our pulse rates, what we move over, okay? Now, notice when we're setting it for a confidence interval, we do not have to set up the hypotheses test here. We're simply setting our confidence interval for mu. And so with an alpha of 0.01, we have a confidence interval of 0.99, right? So, because again, our alpha and our confidence interval are related to each other. So if we have an alpha of 0.01, our confidence interval would be 0.99. If, for example, we had an alpha level of 0.05, then our confidence interval would be 0.95. Usually the default is set at 0.95, so be careful if you're solving for a problem with a different alpha level. You're going to need to come in and set that yourself. Once you have that set, you hit compute, and you should get an output that looks a lot like this. And this gives us our limits. So our lower limit, as we can see here, is 72.553. That's rounding to the third digit. And then our right is going to be our upper limit, 82.447. So that gives us our lower limit and our upper limit, or if you're diagramming it out, may help you to think about it as being your left and your right. Okay, now we're moving into doing our interpretation. And our interpretation rule is asking, does the assumed value of mu fall within the interval boundaries? So if we're setting this up as a type of numeric equation, it's going to look something like this one down here. So it's going to have lower limit, or our left-hand value, is less than our mu, and our mu is less than the upper limit, or the right-hand value. That is the language that we need to set the problem to. So if we take the different pieces of information we have, we plug these in, we should get something that looks like this. Notice there's my mu back from my null, right? 76, that's what goes there because that's what we're asking the question about, okay? So remember, we're always asking about the mu. We're testing the mu, right? And then we plug in, there's our left-hand value and our right value. So once we have this set up, we ask ourselves, is this a true statement? Okay? If it is a true statement, then we fail to reject the null. If it is not a true statement, then we reject the null. Now notice this interpretation rule is different than the one for the p-value. Okay, so we're asking a similar, having a question that we're answering here, but keep in mind the rule for the interpretation is very different for the confidence interval than it is for when you're looking at a p-value. So be very careful about that. So looking at this problem, and we asking this question, does 76, is that fall within our two limits? So is it true to say that 72.553 is less than 76, and that 76 is less than 82.447? And if it's true, yes, that is a true statement, then that means that we in fact fail to reject the null hypothesis. This is because the standing value of 76 does fall within those two parameters at a confidence level of 0.01%, confidence interval 0.99, okay? That means we can be a 99% confident that our value of 76 actually falls between these two norms, okay?